Now we discuss numericals to find characteristic polynomial of a linear transformation and then verify Cayley Hamilton theorem. So here, to find characteristic polynomial, we proceed in the similar manner that we discussed in our previous lecture. So here we can discuss again. We start with the standard basis, that is 1 0 0 0 1 0 0 0 1, and first we convert this transformation into its matrix, that is T of B, and to find this we write the image of every element of the basis and then express that image as a linear combination of these elements, which comes out to be T of 1 0 0 equals 1 0 1 1 times 1 0 0 After writing these linear combinations, we know the matrix of T relative to B is the transpose of coefficient matrix. So this is the coefficient matrix, and taking its transpose we get this, and we let this is our A. Now characteristic polynomial, delta T of T is determinant of Ti minus A, that is T minus 1 minus 1 0 0 T minus 1 minus 1 minus 1 0 T minus 1. So expanding, taking the determinant, we left with T minus I square minus 0 minus of 1, which further imply delta T is T minus 1 cube minus 1. So opening this cube, T cube minus 3T square plus 3T minus 2, which is the required characteristic polynomial to verify Cayley Hamilton theorem. So we will see whether T satisfy this. As we proved in the theorem, we need to prove delta T is 0. So here delta T will come out to be T cube minus 3T square plus 3T minus 2I. So we are given T. From this T we will find T square and T cube, and then put those values in this equation. X, Y, Z is this. From this T we can easily find T square by taking T of T x y z, putting T x y z here, then again applying transformation on this, we get this, and repeating the same procedure to find T cube. T cube is T of T square, so putting this value here and again applying T on these terms, so we get this. Now putting all these terms here, that is delta T of x y z, that is T cube of x y z, 3T square of x y z, 3 of T of x y z, 2 of I of x y z. Putting all the values and simplifying, we can easily see that this will comes out to be 0 0 0, which is zero operator of 0 0 0, which proves delta of t is 0. So hence Cayley Hamilton theorem is satisfied. Find characteristic polynomial and using Cayley Hamilton theorem find A inverse. So we are given a matrix. So from a matrix again we will apply the method to find characteristic polynomial, that is determinant of ti minus a equal to 0. A is an identity matrix of order 3 cross 3 and A is the given matrix. So putting all the values we get t minus 2 1 minus 1 1, t minus 2 1 minus 1 1, t minus 2. To find determinant we will first simplify this determinant by applying some operations on column 1 c1 plus c2 and on column 2 c2 plus c3, which will reduce this determinant into the form adding these two columns t minus 1 0 and here 0 t minus 1 t minus 1 minus 1 1 t minus 2. Minus 1 common from column 1 and column 2 we have t minus 1 square 1 1 0 0 1 1 minus 1 1 t minus 2 equal to 0. So expanding the determinant we are left with t minus 1 square into t minus 4. So further multiplying we have t cube minus 6t square plus 9t minus 4 equal to 0, which is the required characteristic polynomial. To find A inverse we use Cayley Hamilton theorem. That is delta of A equal to 0, which further imply a cube minus 6a square plus 9a minus 4i equal to 0 matrix. And by the corollary of Cayley Hamilton theorem we can have 4i equals a cube minus 6a square plus 9a, which further imply A inverse is equal 1 by 4 a square minus 6a plus 9i. Now to find A inverse we find square of the matrix, that is a square. A into a is this. Putting these values a square, a and I and solving we will get the value of this expression, and putting it back here we will have A inverse 1 by 4 times this matrix. In next question we are given a linear operator and question is to find characteristic and minimal polynomial. So we will proceed in a similar manner to find characteristic equation. Given tx y z is this. First of all we start with the standard basis b, and from that standard basis we will convert the transformation into its matrix, that is TB. So I am writing it here. That comes out to be 1 1 0 0 1 1 0 0 1. Now from this matrix we can write its characteristic polynomial. If we let this is a, then characteristic polynomial is determinant of ti minus a equal to 0, and which comes out to be t minus 1 cube equal to 0. Now to find minimal polynomial, and Now to find minimal polynomial, as characteristic values of t are the roots of minimal polynomial, and minimal polynomial is a polynomial of least degree satisfied by t. So the possible minimal polynomials are factors of characteristic equation, that is t minus 1, t minus 1 square, t minus 1 cube. Now we will check one by one. First we check t minus 1. For this we will see that whether t satisfy this, that is t minus I of xyz, which is txyz minus I of xyz. txyz is x plus y, y plus z, z minus xyz, so which comes out to be y z, which is not equal to 0 0 0. So t minus I or small t minus 1 is not a minimal polynomial. Now we discuss second part, that is t minus I square xyz. Now we will check whether t minus 1 square is a minimal polynomial. So again we will replace small t by capital T, and then here by I, t minus I square xyz, and we already have t minus I, so we will have t minus I of xyz, so that is t minus I of, and which is y z 0. So t minus I of y z 0, that will comes out to be, so from this result using the symmetry, so this is y z 0, so this will be z 0 0, which is again not equal to 0. Now we will check third, t minus I cube xyz, that is t minus I of, which is 0 0 0. Hence t minus 1 cube is minimal polynomial.